Alrighty, folks. So, today we're going to be doing our last section for this semester, and it's section 8.4. So as a reminder, up here at the front, this section comes later on in our book. It comes after the sections on integrals. And here in Calc 1, we're not dealing with integrals, right? So anything in this section that talks about integrals, don't worry about it. It's not going to be involved in any of the problems we're doing. We're just going to be dealing with the definition of the Taylor polynomials themselves, right? Because that's what all this section is about. And the Taylor polynomials, all you need to do to actually understand them is understand the derivative, right? So the nth Taylor polynomial around a of f of x, so there's lots of little bits to go with it, is, so t sub n of x is telling us we're dealing with the Taylor polynomial. The linear term is f of a. The constant term is f of a. The linear term is the first derivative of f of a divided by 1 factorial times x minus a. The quadratic term is the second derivative of f at a all over 2 factorial times x minus a squared. And I didn't leave myself quite enough room, so I'm going to use the cheating power of my drawing pad to give me some extra room, because I just need a little bit. And then we keep that going until we get to the nth term, which is the nth derivative at a. Okay, so it's still sort of sloppy, but it's the same sort of pattern. We just have an n instead of the numbers, right? So what this is, well, for one, let me finish defining some terms first. If a equals 0, it's a Maclaurin polynomial. Right, or rather, if it's a Maclaurin polynomial, it's a Taylor polynomial around 0. So sometimes when you're given a question, you won't be told what a is, you'll just be told that you want to find a Maclaurin polynomial, and that tells you that a equals 0. Right? So in the past, we've had a couple little bits where we've talked about linear approximation. And this isn't linear approximation. As you'll note, that's a very non-linear function. But it's like linear approximation on steroids. And in fact, T1 is the linear approximation that we talked about before, right? But T2 is basically a quadratic approximation. T3 is a cubic approximation. T4 is a quartic approximation, right? And the idea there is that t sub n of x is always going to be approximately equal to f of x, and the bigger the x, or bigger the n rather, the closer it is. Right, so the linear approximation is fairly close in a nearby region. The quadratic approximation, T2, is going to be even closer. The cubic approximation, T3, is going to be closer still. So on and so forth, and every n is going to get something that's closer and closer and closer. Right, but how we find it is we just use this formula, and that's mostly what we're going to be talking about in this class, right? When all we have is the derivative, we can definitely find the Taylor polynomial, but we can't do a whole lot of stuff with it. So before we hop into problems, however, I wanted to clarify some notation. Again, n factorial means you start with n and then you multiply the next number down, and then the next number down, and then the next number down, all the way until you get to 1. Right? So just as a reminder about that. Also, the other way to write the nth Taylor polynomial is using sum notation. So we're going to start with 0 to n of f, the ith derivative of f at a, all over I factorial times x minus a to the I. Right? So, and as a reminder about what this notation means, it means that you start at 0 and you plug in I equals 0 to this guy, right? And that gets you this. Then you add what happens when I goes to 1. You plug 1 here, which is what you get to this, and you add it to what you had before. Then you let I go to 2, which, at least for this formula, means you get this, and you add it to what came before, right? And you do that over and over again, and I goes up by 1 each time. It's 3 next, and then 4, 5, all the way up to n, right? We stop at n, we plug in for I into this formula, which gets us this. We add it to everything that came before, and that's our Taylor polynomial, right? So this is a more efficient notation. But it means exactly the same thing as what comes up here, right? It's just writing sort of all of them down at once rather than one at a time with some dots, right? So let's find t sub 3 of x for f of x equals 1 over 3 plus x around a equals -1. Right? So, if we think about t3, right, that's going to be the sum from I equals 0 to 3 of the ith derivative at a, which we know what a is, so we can go ahead and plug that in, all over I factorial times x minus a to the I. Right, so this is going to be, if we do all this out, this is a step you can skip in general. I'm just doing it so we can get some practice with that sum notation and making sure we understand what that means. Right, so first we need to let I equal 0. So here the 0th derivative is just the function itself. And 0 factorial is always going to be 1. Right, then we need to add and let I go to 1. So we're looking at the first derivative of -1 over 1 factorial times x plus 1 to the 1. I'm not going to have enough room again. Taylor polynomials just take up so much room. Let's see if I can't write a little smaller. Right, so we did it with 1. We need to let 1 go to 2. So we get the second derivative for 2 factorial of x plus 1 squared. Right, then we need to let I go to 3, and that's where we're going to be able to stop. So we have the third derivative over 3 factorial times x plus 1 cubed. Right? So we have all of these pieces, except we need to figure out all 3 derivatives, right? So first we need the first derivative. So I'm going to go ahead and write f of x as 3 plus x to the -1, and that's just because I prefer using the chain rule and maybe the product rule over using the quotient rule. If you prefer the quotient rule, you can absolutely do it using the quotient rule. But I'm going to do it this way, so I know that f prime of x is going to be negative 1 times 3 plus x to the negative 2, using that generalized power rule, times the derivative of the inside, but the derivative of the inside is just 1. Right? Now I'm going to do the second derivative, and again I can use the generalized power rule to get this guy. And again we need to multiply by the derivative of the inside, but that's still just 1. And lastly, the third derivative, we're going to again use the generalized power rule. And again, multiply by the derivative of the outside, but that's just 1. Right? Now, whoops, I forgot to write that we knew what a was in most of these. Right? So now we can actually plug stuff in. So let's find f of negative 1, right? Because we're going to need that for here. That's going to be 1 over 3 plus negative 1 is 1/2. The first derivative of negative 1 is going to be negative 1 over 3 minus 1 squared. So it's going to be negative 1/4. The second derivative at negative 1 is going to be, where'd it go? Here it went. 2 divided by 3 minus 1 cubed. So that's going to be 2/8, which is 1/4 again. And the third derivative of negative 1 is going to be negative 6 divided by 3 minus 1 to the 4th, which is negative 6 over 16. So that's 3/8. Right. Okay, so we have all those values. Now we just need to plug some stuff in. Right, so we know that T3 of x is going to be f of negative 1 divided by 0 factorial, so that's just 1/2 divided by 1. Right, and this goes away because anything raised to the 0th power is just 1. Now we need to have f prime of negative 1 divided by 1 factorial times x plus 1 plus the second derivative at negative 1, which is positive 1/4, over 2 factorial. I really should have just said 1 factorial is just 1. It's a very small eraser. 2 factorial is also 2. We get to some exciting ones in a second. And then we need the third derivative at negative 1. So negative 3/8 divided by 3 factorial is 3 times 2 times 1. So that's going to be 6 times x plus 2 cubed. And now I just want to simplify a little bit. So we get 1/2 minus 1/4 x plus 1 plus 1/8 x plus, I don't know where these 2's came from. They've been x plus 1's all along. Right, if we look up here to our formula, it's just those x plus 1's. Yep. And here, the 6 can cancel out with the 3, but there's a 2 left over. So it's going to be minus 1/16 x plus 1 cubed. So that would be our third Taylor polynomial for the function 1 over 3 plus x around a equals negative 1. Right, now if you have the same function in a different a, your Taylor polynomial will look a little bit different. Right, if you have the same a but a different function, it'll look very different. But so both of those, you need both of those in order to find a Taylor polynomial. Right? So let's do a sort of silly one, but I just want to show y'all how it'll turn out. So find all the Taylor polynomials. Now let's do Maclaurin polynomials. For f of x equals 3x squared plus 2x minus 11. Right. So that means we need to find t1 of x, which is f of 0, right? Because Maclaurin means that a equals 0, right? Plus the derivative of f at 0 all over 1 factorial times x minus 0 to the 1. Right, so that's our t1. That's also going to be equivalent to L, right, if we remember the linear approximation that we called L. But we do need the first derivative for it. So the first derivative of x is going to be 6x plus 2. And so the first derivative at 0 is going to be 2. Right, so here f of 0 is negative 11. Right, so if we plug this in, t1 of x equals negative 11 plus 2 divided by 1 factorial times x, which is negative 11 plus 2x. And one thing you'll note, and this is not a coincidence, this is why I've done this problem, the linear approximation of a polynomial is the linear and less portion of that polynomial, right? 2x minus 11 is the same thing as negative 11 plus 2x. Right, now if we wanted to do the second polynomial, that's going to be f of 0 plus f prime of 0 divided by 1 factorial times x minus 0 to the 1, plus the second derivative with 0 plugged in all over 2 factorial times x minus 0 squared. So we need to know what the second derivative is. Right, so that's going to be the derivative of this guy, which is pretty easy. And plugging in 0 is similarly easy. So we get that t2 of x. And note that one of the things we could have done is that this is just t1 of x, right? This stuff here, plus 6 divided by 2 factorial times x squared. So that's negative 11 plus 2x plus 3 times x squared. And hey, what do you know? T2, the quadratic approximation of a polynomial, is the quadratic terms and less. Right? Now, T3 is a little bit silly, right? I'm going to write it as T2 of x plus this third derivative of x at 0 over 3 factorial times x minus 0 cubed. The reason it's silly is because when I take the third derivative of f, I get 0 out of it, right? So when I plug 0 into it, I still get 0 out of it. So T3 of x is really just T2 of x by itself, right? And that's going to be the case, right? The way Maclaurin polynomials, Taylor polynomials work for polynomials is that they are always just going to be that portion of the polynomial, right? The linear Taylor polynomial is going to be the linear and less portion of the original polynomial. The quadratic Taylor polynomial is going to be the quadratic or less portion of the original polynomial. And after the degree of the polynomial is reached, so after you reached square, all of your Taylor polynomials are going to be the same. right? Because there's not going to be any bigger terms to pick up. So finding the Maclaurin polynomials or the Taylor polynomials for a polynomial is a little bit silly, but also very easy, right? So I just wanted to point out that that is an intended thing, right? The polynomial approximation of a polynomial is just the original polynomial that you started with, because you can't get closer than the original thing, right? So lastly, find the general form for the Maclaurin polynomial of e to the 2x. Right? So what the general form means is that it wants you to find a formula, a simpler way of writing down without any derivatives involved, of this, right? Of this nth one. A here is going to be 0 again because we're a Maclaurin polynomial. Right, and so basically what that means is it would like you to find a nice way to express this, right? So that means we need to take a couple derivatives and see if we can find a pattern, right? So f of x is e to the 2x. So f of 0 is e to the 0, which is 1. And this is what happens when n equals 0, right? We're going to be trying to find a pattern, so we need to keep track of what n looks like. Right? F prime of x, right? This is using our generalized exponential rule. We're going to take the derivative of the exponent, which is just 2, and multiply it by e to that exponent. So we get that guy. F prime of 0 is going to be 2 times e to the 0 is going to be 2. And this is what happens when n equals 1. The second derivative of f is going to be we're going to do that same thing where we pull the derivative of the top out. So that's going to be 2 multiplied by the 2 that's already there. Then e to the 2x stays here. So f prime of 0 equals 4 times e to the 0 equals 4. And I don't know about you, but I'm beginning to see a pattern. But let's do one more just to make sure. Right, so when we do 3 derivatives, we're again going to use the generalized power rule and the constant multiple rule to get 8 e to the 2x. So the triple derivative of f at 0 is going to be 8 times e to the 0, which is 8. And so it certainly looks like that this is 2 to the n, right? Because if you have 2 to the n when n is equal to 0, you should get 1. 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8. And if we think about it, using that generalized power rule, we're always going to be bringing another multiple of 2 in it at each step, right? So it makes sense that this just means multiply it for another 2 by each n, right? So the answer to this question is just going to be Tn to the x equals the sum I equals 0 to n of 2 to the n divided by n factorial times x to the n. Right, so that's all that type of problem means, is figuring out a way to take this piece of it, the derivative piece, and write it as just a formula with n in it, right? So that you could use this formula without having to know anything more about it, right? Without having to know the function, without having to take the derivative yourself. You can just start to plug this in and get some values out of it, right? So that's what this general form means. Okay. So those are the types of problems that will be taken from these. Remember again, hopefully you haven't gotten all the way to here and missed all the other times I've said it and thus be really frustrated, but don't worry about any of the derivative stuff in this section. Just worry about the definitions and the examples where they figure out what the Taylor polynomials are, and evaluate them, right? Don't worry about the integral stuff. Don't worry about the error stuff. Just about basically what the definition is, how to use the definition, and how to find these individual Taylor polynomials. So that wraps up the semester, so I guess I can't say see you next time. There will probably be another problem or session 2 after this, though that's going to be far in the future for me at least. So yeah. I guess maybe I should say have a good winter break here. I don't know. This is weird. But this is the end of this mini lecture series.